Hello, quick video on natural logs and exponents and why we've got them and how we use them. So we've looked earlier in the course at powers, haven't we? So here 2 to power 3 is 8, and we can look at the logarithm as the inverse of that. So the log base 2 of 8 is 3, which is the sort of reverse, isn't it? Let's read it as we should. What power must we apply to 2 to get the value 8? And the answer is we must apply 3. And of course, we're probably more used to doing this in tens, aren't we? So 10 to the power 3 is 1,000, and therefore the log to base 10 of 1,000 is 3. And of course we have on our calculator buttons to help us do this. So here in this area here we've got our log function. There we go, log, and on that same button we've got 10 to the power x. Now what's interesting is what have we got beside it here? We've got a button that's got ln on it, and above it it's got a symbol e to the x. And that's what we're going to deal with in today's video. So the ln function is called the natural log, and the ex is the exponent, and both of those are related to this irrational number, a new irrational number, and a transcendental number, a bit like pi. And this appears in nature, and we're going to use it in that way. So we've got this number e, which is 2.718 and all these other numbers, and it turns out that we can find this through our calculations and use it a lot. So where does this number e come from? Well, it's a transcendental number, a bit like pi, and it has an extraordinary quality useful in differentiation, which we've done in this course. That if we had a function which is e, that number there, to the power x, in exactly the same way that was like 2 to the x, yeah, but e to the x, then if we differentiate that, we find that we're back at the function we started with, e to the x. So it's its own differential, and the important thing therefore, remember, our differential is our gradient, yeah. So if we found the value, y value at any point, then the gradient's going to be the same in e to the x. So we can have a look at this by looking at some graphs, and we'll use GeoGebra to do that. So here, this green line is the graph of 2 to the power x. So that's y equals 2 to the x. So when x equals 1 here at this point B, there, then y is going to be equal to 2, isn't it? And when x equals 2, y is going to be 4, and when x equals 3, y is going to be 8. Yeah, because it's just 2 to the x. We can in here have a look at, we could find what the gradient is at this point. Let's do that. And we find here the gradient of the tangent at that to the curve at that point, that's our little triangle there, is 1.39. So the gradient, whereas y is 2, so the gradient's under the value of y, isn't it? And if we divided the 1.39 by 2, the value of y, we would get a value of 0.69. And if I moved this point, this m point, this B point along, so if I moved it up here, excuse me, I'm going to try and move it here, come on, off we go. I moved it along, there we go, apologies, a bit slow there. We've now got y is 4, and we've got our gradient m is 2.77. And if we have a quick look at it, we can see that 2.77 divided by 4 is going to give us 0.69 again. And if we go up to x, what x equals 3, we've got y is 8 now, and we've got a gradient of 5.55. So if we get our gradient 5.55 and divide it by 8, we're going to find we're back at a number or 0.69. So all these are in ratio. So if we were to have a quick look and we tabulated those results, here we go, in the green table here, we find that the ratio between the y value and the gradient at that point all the way through here is 0.69. 0, 1, 2, 3, any x value, yeah? It's always some sort of ratio scalar. Okay, let's have a look at what happens if we look at y, a different function. Y is 10 to the x. So here is the curve of y equals 10 to the power x. So obviously when x equals 0, y equals 1. And if we look at our little tangent triangle here, we've got the gradient is 2.3. So again, if we take our gradient divided by our y value, 2.3 divided by 1 gives us 2.3. Let's move the point along up to x equals 1, and excuse me, our picture's gone off, our triangle's gone off the top of the screen there. So now we've got x equals 1, y equals 10 here, and the gradient is 23.03. So we've got 23.03 again divided by 10, so that's our gradient divided by our y value. We're back to 2.3. So if we were to tabulate those values in the same way, our x, for each of our x values, x equals 0, 1, 2, let's have a quick here. So if we tabulate it for 0, 1, 2, 3 and 4, we can see our y values pretty quickly, isn't it? Because 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, and 10 to the 4 is 10,000. And our gradient, the first one is 2.3. For x equals 1, the gradient's 23. And for x equals 2, it's 230. And for x equals 3, it's 2,302, all the way up to 23,025. And if we divide the gradient by the y value, we get a constant 2.3. Yeah. So if we looked at that on the graph, we could compare the original curve, here's that the blue line for y equals 10 to the x, with the gradient for that curve. So let's put that on the screen. There it is. It's that blue dotted line. So for each point here, the gradient is higher by a multiple of 2.3 by ratio than the x value. So that's always above, isn't it? The gradient's always above the value of y. If we go back to y equals 2 to the x, that's the green line, and we put the gradient of that on, we found that the ratio was 0.69. So for each point here, the gradient is slightly lower than the value of the y, isn't it? So therefore the green dotted line is below the whole time, and the blue dotted line, the gradient of that one, is above the whole time. Now what really interests us is, I wonder what point, what the value is. That was an exponent, the green one's an exponent of 2 to the power x, and the blue one is a 10 to the power x. So what number, rather than 2 or 10, would result in those two lines falling on top of each other? So the gradient actually lies on top, it's not above or below. So should we have a go at that and see what we come up with? So let's let the base be a value a, yep, and let's draw a graph of a. There we go. Here's the red line is going to be our graph, and there's our value of a on this line at the top. There's 1.1. Let's move it up to around 2, shall we? So that is, we can see here that the red line is now on top of our green line, so we're on y equals 2 to the x, yeah? And if we wanted to look at the gradient of that curve, we can get GeoGebra to find that. There we go, and that's come on top of that's dropped on top of the gradient of 2 to the x. Now if I start moving a, if we moved it down, here we go, we can see those going down, and the gap between the gradient is getting larger, isn't it? So we actually want to go up. Here we go, and as we increase the value of a, so now we're at 2.2, we can see those lines getting lines getting closer together, can't we? The original value function and its gradient. And as we move up to here, they're almost exactly the same place now, yeah? And can we see that a is now 2.71? And if we start going above that, we see that the gradient's getting is now greater than the value of y, yeah? So there is this point where the two coincide, and that's the fundamental idea of natural logs and natural powers, is that this value of a, which here we've got at 2.71, results in this property that the exponential function becomes its own gradient, and that's going to prove to be extremely useful in our higher level maths when we're doing differentiation, because what's really useful is to have a function that is its own differential. So there we go. So we can see here by that little experiment that our value of this is going to be about 2.71. Yeah, 2.71. That's the value at which y equals a to the x, that the gradient will be the same as the y value, yeah? And we get this value, if we did it, it would be 2.71828. And we define that, we're going to give it a name because it's really useful to us. We're going to call it e, a bit like we called 3.1416159 rather, we called that pi, didn't we? Here we're going to call it e. It's also known as Euler's number. If you wanted to get an exact value of it, we could from this series here, because actually that value of e is 1 divided by the factorial of 0, add 1 divided by the factorial of 1, add 1 divided by the factorial of 2, add 1 divided by the factorial of 3. So that series, that would give us this number exactly. Okay? And the only other thing for us to look at today is terminology. So we have ways of writing this exponential when we're using this value 2.71, and we either write, if we're doing exponentials, we go y equals e to the x, yeah? So rather than putting a 2 to the x or a 10 to the x, we just write e to the x. And if we want to find our natural logarithm, we would call that ln, log natural of x, which is effectively the log to base e of x, yeah? And as we saw earlier, we can see that on our calculator. Here it is. It was that one on this side here, wasn't it? Our ln button. So we can do all our calculations in natural logs. There we are. Very quick summary of the situation. Natural exponents or logs, exponents and logs are written in this form. Y equals e to the power x, and ln, log, natural log, ln of x is log to the base e of x. The value of e that we're using here is Euler's number. Euler's number, there it is. And it's this really long irrational number, 2.71828, etc. And the most important thing about all of this mathematically is that if we take the function e to the x and we differentiate it, we get the same function. We get e to the x, and we're going to use that in solving lots of differential equations. So there we are. I hope that's of use.